Yeah, so anybody else wanted to solve anything today? Oh, I'll wait a little longer. All right, so yeah, so let me go on. The next thing in Harari's book is there's a chapter where he introduces profinite groups, and then he introduces sort of cohomology of discrete modules over profinite groups, okay? And I just decided, so he has an introductory section on profinite groups, and I felt that what he was saying was he was not exposing the full glory of profinite groups. And so I want to give just like a kind of, kind of interregnum lecture on profinite groups, or a short lecture. And then I have I added a bunch of problems in the problem set. I just posted that on profinite groups. And so maybe I'll say my piece. It looks like I think I have maybe 3 pages. Yeah, I just have 3 pages of notes here on profinite groups, and then they'll kind of set up some of these exercises. And I think, among other things, these are meant to be some interesting, not super technical homework problems that you guys can do for the rest of the course. Okay, so yeah, and then the rest of chapter 4, it's kind of spade work again. So you want to set up your cohomology theory for discrete G modules where G is a profinite group, and I want to go through that quite quickly, just because it's similar to what we already did, and we really want to get on to the contentful part of Galois homology, which is very interesting, and then we want to move on to local class field theory. So, yeah. Okay. So right, so some remarks on profinite groups. Here goes. So I remind you, there's a certain nice class of topological spaces, sometimes called profinite spaces, sometimes called stone spaces. I feel like there's even other synonyms for them that I'm Boolean spaces, sometimes called those. Yes. There's even a stone duality. There's a categorical equivalence between. Anyway, these spaces are compact, which includes Hausdorff, and totally get disconnected. Equivalently, they're an inverse limit of finite discrete spaces. Yeah, and so stone duality, among other things, gives a categorical equivalence between the category of such topological spaces and the category of, well, Boolean rings, for instance. So commutative rings in which each element is an idempotent. And so then if you just take a Boolean ring is 0-dimensional, so you just take the prime spectrum is every prime ideal is maximal. And if you remember from commutative algebra, if your ring is 0-dimensional, then the prime spectrum is always a separate. Actually, I think is always a Hausdorff topological space if the ring is 0-dimensional. And in fact, if you take the spectrum of a Boolean ring, then you get a compact, totally disconnected topological space. Anyways, this is a very important class of topological spaces from various perspectives. They are the compact, totally disconnected spaces, which it's a theorem. It's easy to see that an inverse limit of finite discrete spaces is compact and totally disconnected. That's just an easy exercise in working with inverse limits. Okay, basically it's going to be a closed subspace of a product of finite discrete spaces. So it will be compact by Tikhonov's theorem, and products and subspaces of totally disconnected spaces are totally disconnected. So that's the easy direction. In the other direction, if I give you a compact and totally disconnected space, you need to figure out how to make it an inverse limit of finite discrete spaces. Okay. And so then a profinite group is basically a group object in this setting. So it's a topological group whose underlying topological space is compact and totally disconnected. I guess it doesn't immediately follow from what I just said. So therefore, a profinite group, the underlying topological space is an inverse limit of finite discrete spaces, but surprise, surprise, in this case, you can do that compatibly with the group structure. So any compact, totally disconnected topological group is an inverse limit of finite discrete groups. Okay. So that's what a profinite group is. That's a very, very, very important class of groups. Of interest to various, in several different parts of mathematics. In pure group theory, profinite groups are of interest. Okay, so quick exercise here. In any compact topological group, a subgroup is open if and only if it's closed to finite index. Okay, in any topological group, an open subgroup is also closed. Okay. So that's a character that's giving you a relationship between in a compact. Yeah, okay. So in any topological group, an open subgroup is closed because its complement is a union of cosets, each of one of which is homomorphic to itself. And in a compact group, an open subgroup must have finite index. Again, just using the partition into cosets. On the other hand, that's not very hard at all, but you have to there's a mistake here that you need to not make. So no one said that I'm telling you that every open subgroup of a compact topological group has finite index. I am most certainly not telling you that every finite index subgroup of a compact or even profinite group is closed. Okay, is open or equivalently, since it has finite index, closed. And so now let me show you an exercise where there's a very standard example of this. I mean, there's lots of examples, but okay, where did it go? Yeah. So yeah, now let me go back and share. There we go. Yeah, so see, there's a new section on profinite groups. The first few exercises are on topological groups in general, so just some kind of reasonable stuff. Most topological groups in practice are Hausdorff, and if you don't have a Hausdorff topological group, if you mod out by the closure of the identity, then that will give you a Hausdorff topological group. So pretty much you can assume that everything is Hausdorff. Okay. Right, this was the exercise that we just mentioned. Okay, so here's the interesting example, and it doesn't have to be this. This is just the simplest example. So just take the direct product of countably many copies of F2 or Z-mod 2, make them and give each one the discrete topology and put the product topology on it. Okay, so this is evidently a compact, totally disconnected topological group. So it's a profinite topological group. Here's what you have to show. The number, there are some obvious open subgroups, right? So if I take the subgroup that consists of 0, 1 in all factors but 1, and then in the last factor I require the coordinate to be 0, then that's an index 2 subgroup. Okay. And so that those subgroups are open immediately by the definition of the product topology, right? So it's pretty, you can visibly see a countable infinite number of open subgroups of index 2, each one of which is itself a Cartesian product, right? It's not super hard to show that in fact the total number of open subgroups is countably infinite. On the other hand, this is an F2 vector space. It really is. Okay, and so look at the set of index 2 subgroups, equivalently codimension 1 subspaces of the subspace. Here, because it's the field of 2 elements, things are especially simple. And so I claim there's a pretty easy bijection between the set of all codimension 1 subspaces and the non-zero F2 linear functionals. Okay. Whenever you have a non-zero linear functional on any vector space over any field, the kernel gives you a subspace, but because the field is F2, if you know the subspace, then you know when your linear functional is equal to 0. if you know the kernel, you know where it's equal to 0. The only other value it takes is 1. So over F2, knowing the kernel of a linear functional determines the functional, whereas in general, it would determine it like up to scaling or something. Okay, so there's literally a bijection between index 2 subgroups of this group and non-zero elements of this of the dual space. And the dual space of a vector space always has larger dimension than the vector space if the vector space is infinite dimensional. Okay, that's a graduate level linear algebra fact. Okay, and so you don't even need that, I guess even certainly the vector space injects into its dual space, and this is an uncounted. It's not a direct sum; it's a direct product. So the dimension of this thing as a vector space over F2 is uncountable, and the dual space is certainly larger, at least as large as the original space. Anyway, so the total number of index 2 subgroups is uncountable, whereas the number of open subgroups altogether is countably infinite. And if you want to be really precise about it, there's a ridiculously large number of index 2 subgroups. It's 2 to the cardinality of the continuum, so 2 to the 2 to the Aleph naught. Okay, so there's like a ridiculously large. If I pick an index 2 subgroup at random, boy, is it probably not going to be open because I only have countably many open index 2 subgroups, all of the obvious ones. And then the magic of linear algebra gives me many, 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 many more index 2 subgroups that are not open. Okay, this was, I really thought that this was true. I remember when I was a postdoc, I had a conversation with a grad student at McGill, and like he just kept, I mean, he was right and I was wrong. And I was just like, but of course every finite index subgroup is open. And eventually he made me see that I was wrong. Okay. But that's actually kind of important in the study of profinite groups. Okay, so wait, did I back to sharing the screen? Okay, yeah. All right, let's proceed. Yeah, so a subgroup of a profinite group is profinite itself in the subspace topology if and only if it's closed. That's almost obvious. Every closed subgroup of a profinite group is the intersection of the open subgroups containing it. That's less obvious and is a nice fact. So if you know the open, basically the idea of a profinite group is that it's, if you know what the open subgroups, it's a compact group so that if you know what the open subgroups are, then everything else is determined from those. And so literally every closed subgroup is the intersection of the open subgroups containing it. Okay, so now we have a notion of profinite completion. I had just been thinking a lot about like completion functors in the category of topological spaces just for my own, I don't know why, but I have recently. So I decided to mention that you can take the profinite completion of any topological space. So what does that mean if you want to be categorical about it? The forgetful functor that just takes a profinite space and says, well, in particular, it's a topological space that has a left adjoint. Okay, and so that's a certain type of completion. So that's called a reflective subcategory, if you want to be fancy about it. But it has a familiar universal mapping property of a type of completion. So what does that mean if you learn, if you unpack this left adjoint to the forgetful functor business? What does that mean? It means that for any topological space, there's a profinite space, compact totally disconnected, a continuous map from your space into the profinite space, which is universal for continuous maps from X into any profinite space. Okay. And this is not, I mean, I actually found there's like a general condition for a class of topological spaces to be, for a subcategory of a topological spaces to be a reflective subcategory, and this the condition does apply here. I think if your class of topological spaces is like closed, if you have a property of topological spaces that passes to products and passes to all closed subspaces, then in general, you can do this thing, and that is true, as we just talked about. A product of arbitrary product of profinite spaces is a profinite space. A closed subspace of a profinite space is a profinite space. So good. Okay, but we can be much, and again, I'm not telling you exactly what it is. I'm not sure that it has as down to earth a description as it does in the case of topological groups. If you have a topological group, then you probably don't define the profinite completion in categorical terms. You define it via a specific construction. But before I say that, the literature is really bad about this, and that causes confusion. Here I'm defining the profinite completion of a topological group, okay? So if I have a group and it doesn't have a topology, I can still make use of this construction by saying, if your group doesn't have a topology, don't worry, give it the discrete topology, okay? But many people, when they say profinite completion of a group, they mean put the discrete topology on it, and then do this topological group profinite completion, which is fine, except sometimes people do that when they already have a topology on the group, and then that's confusing. You should say profinite completion of the associated discrete group. Anyway, so if you have any topological group, again, there's a universal map into a profinite topological group, and now I can say exactly what it is. You just range over all open normal subgroups of your topological group. Goodness. That doesn't sound right. This sounds like I should tack on finite index. Open normal subgroups of finite index. If the group was compact, then as we just said, the finite index is automatic, but I definitely want these quotients to be finite, so I better require that, yeah. Okay, so I range over all open normal subgroups of finite index. If I take the quotient, this is going to be a finite, with the quotient topology, then this is going to be a finite discrete topological space. And then I take the inverse limit, and that will give you a profinite space. Let me just think for a second. Perfect, yeah, okay. So that's the profinite completion of a topological group. So you sort of, the only thing you care about are what are the, it only takes as data the open finite index normal subgroups of your topological group, and you do this. Okay, so it's pretty clear. What's clear? It's pretty clear that this is a profinite group. It's an inverse limit of finite discrete groups. It's not so hard to see. There's certain, I mean, by the universal property, the inverse limit, there's certainly a natural map from G into this inverse limit. It's going to be continuous. The fact that this actually satisfies the universal property up here, probably takes, I'm not saying that's obvious. You have to check that. Okay, so let's see. See ya. All right, I'm taping it. It'll be fine. Okay, so again, it's also pretty clear that that the image of the group and its topological group and its profinite completion is dense. Okay, so its closure must be the whole thing. Why? Well, if you didn't think it was dense, take the closure of the image instead, and you can see that if the whole thing satisfies the universal mapping property, then all you would need would be the closure of the image. That would also, everything would map through that. So it's pretty easy to see that. The group is, the image of the group in its profinite completion is dense. The warning here is that this map might not be an injection, right? So it would be nice if your completion map was an injection, but it doesn't have to be, okay? And in fact, there are sort of two different problems that you could have here. First, you could have topological problems, right? So the fact that G actually has a non-discrete topology could be causing its own problems. So for instance, what if G is a connected topological group, which is like at the other extreme of a profinite group, but like a Lie group, a connected Lie group would be a great example of a topological group. Well, then of course the continuous image of a connected space is connected, and so therefore IG is connected, but IG is living inside a totally disconnected space. So IG would have to both be connected and totally disconnected. So IG would have to be trivial, but IG is dense in this Hausdorff topological group, and so therefore the whole thing is trivial. Okay, so if your topological group is, in particular, I mean, maybe what's the in general, I mean, more generally, the connected component of the identity in any topological group is going to be a closed normal subgroup, and the profinite completion is going to kill that. Okay, so the profinite completion just totally collapses connected topological groups. Okay, so the profinite completion of the real numbers, for instance, is certainly trivial. Okay, so that's a topological problem. You could also have group theoretic problems. So for instance, suppose that G is discrete, but suppose, as we were looking at earlier today, it's a divisible commutative group, like Q mod Z, or like R, even if you make it discrete, right? Well, a divisible commutative group has no proper finite index subgroups. I promise. That's an easy algebra exercise. Okay. And so, well, if you have no proper finite index subgroups, then your profinite completion has nothing to grab onto, and then the profinite completion is definitely trivial. So yeah, so the profinite, that's a second reason. Without, even if you took R and put the discrete topology on it, its profinite completion would still be trivial because it's divisible. Okay, so there's a name for this. A discrete group is called residually finite if the map into its profinite completion is an injection. You can unpack this a little bit. What does that mean? It means that every non-identity element of the group maps non-trivially into some finite quotient of the group. So that means if I give you any non-identity element of the group, there's a finite index normal subgroup that does not contain that element. Okay, so that's a, when I say it like that, it's like, well, that's clearly a kind of natural group theoretic condition. And so that gets a fun name called residually finite. Yep, okay. And so this is just a very interesting and well-studied condition in all sorts of branches of mathematics. In pure group theory, it's interesting. If I give you like a finitely generated group, it's very interesting to ask whether it's residually finite or not. And it comes up in a bunch of places. Just trying to tell you just trying to make things interesting, a little palate cleanser. So here's a 1993 theorem of Domingo Toledo, which answered a question of Serre, so it's probably a good theorem. So Serre wondered, what if you look at the fundamental group of a smooth projective variety over the complex numbers? Okay, so these are people are interested in fundamental groups of algebraic varieties in general. Okay, even what groups are fundamental groups of compact complex manifolds is an interesting question. And so Serre had conjectured that there's some smooth projective variety out there whose fundamental group was not residually finite, so did not inject into its profinite completion. And this was proven by Toledo. Okay, so the types of groups. So why would you care about whether the fundamental group of an algebraic variety is residually finite? Because if you have a smooth projective variety over the complex numbers, I forget whether I actually need projective here. I have to look up my Gaga stuff. So I'll just say with projective, then you have this étale fundamental group that I guess there was probably a course there was a bunch of stuff about the étale fundamental group, which basically is only, what's the point of the étale fundamental group? This is taking place in the algebraic category. So it's only seeing finite étale covers of the space. And so in other words, if you have an actual topological space, you only look at finite sheeted coverings, and then you take an inverse limit. And so that amounts to the fact that if you had an honest topological space, which you do here, the complex points are a very wonderful space, a compact complex manifold, then it turns out that it's not so deep to see that the étale fundamental group of your complex manifold is the profinite completion of the fundamental group of the set of complex points of the associated space. And so here, if your smooth projective variety is not residually finite, what is that saying? That's really saying that the étale fundamental group is not capturing as much information as the actual fundamental group of the space. right? So the map from the fundamental group into into the étal fundamental group need not be an injection. Okay. All right. Let's see. Right, so for a topological group, the profinite completion map is an isomorphism if and only if the group is profinite. That's guaranteed by the categorical setup. Whenever you have a kind of categorical completion, then anyway, it's true. However, so now I'm hitting a more subtle point. This is what I was talking about before. So if I have a topological group, it has a profinite completion, or I could say, I don't want the topology. I want to consider the associated discrete group and then take the profinite completion of that. Okay, and those are in general, this is the subtle point. Those are in general two different things. Why? Let's talk about it. Because to take the profinite completion of a topological group, you're only quotienting out by open finite index normal subgroups. Whereas if you make your group discrete, everything is open. And so therefore you're quotienting out by, or your inverse system consists of all finite index normal subgroups, okay? So that's the distinction, and there's a word for this. A topological group is called strongly complete if it's isomorphic to its profinite completion as a discrete group. Okay, so let's turn that around a little bit. So if I have a discrete group, this is not completely obvious, but is follows from standard descriptions of profinite groups. This is actually kind of a useful fact in terms of thinking about. If you just consider this map from a group to its profinite completion, and it's probably not a surjection, unless the group is finite or profinite. It may not even be a surjection. However, if you just think of what it does to the lattice of finite index subgroups on both sides, then it is an isomorphism on that lattice. Okay, so if I take a discrete group and I take the profinite completion, then the profinite completion has exactly as many finite index subgroups as the group that I started with does. Okay, so that's a fact. Okay, I mean, again, even more strong. If you have like push forward and pullback maps, if you induce by homomorphism of groups, and I'm saying that if you look at the push forward and you look at the pullback, and you only restrict to finite index subgroups, then the push forward and the pullback give you mutually inverse bijections between finite index subgroups of the original discrete group and finite index subgroups of the profinite completion. Okay. And so if you take that into account, then what do you learn? Well, you learn that every finite index subgroup of the profinite completion of a discrete group is open. Okay, so if I take the profinite completion of a discrete group, I'm probably not getting just any old profinite group. I'm getting a profinite group that does have this stronger property that every finite index subgroup is open. And I just showed you an example of a profinite group that didn't have that property, right? Infinite product of Z mod 2. Okay, so not every profinite group is the profinite completion of a discrete group. In fact, that happens if and only if the group is strongly complete. Okay, so a profinite group is isomorphic to the profinite completion of its underlying discrete group if and only if every finite index subgroup is open. Okay, so that's a subtle point. And now there's just an amazing result in this area. So this was the culmination of lots and lots and lots of work. So it was a 2007 Annals paper of Nikolov and Siegel. If your profinite group is topologically finitely generated, that's defined in the exercises, but a set of topological generators for a topological group, what does that mean? It means if you take the subgroup generated by that set and then you take the closure, you get the entire group. So a subset S topologically generates a topological group if the only closed subgroup containing all those elements is the entire group. Okay, and there's some exercises about being topologically finitely generated. And so it turns out that every topologically finitely generated profinite group is strongly complete. Okay, it's not super surprising that the example that I gave you before was an infinite product, and so that was probably not topologically finitely generated. Can't be by this result. Let me give you a related, this is the last page, by the way. Let me give you a related condition, which is important in number theory. So one says a topological group, usually just restricted to profinite groups, is small if it only has finitely many open subgroups of any given finite index. So if I range over all open subgroups of index 3, there's only finitely many. If I range over all open subgroups of index 12, there's only finitely many. Okay, so that's the definition of small. This is, where am I going with this? Yeah. So for instance, why is this a natural condition? If you apply this to the absolute Galois group of a field, then the absolute Galois group of a field is small if and only if inside a fixed algebraic closure, your field has only finitely many separable extensions of any given degree. Okay, so that's a very natural condition. Okay, and so for instance, I think I made the definition in the exercises. I didn't really like it. So a field is Galois small if its absolute Galois group is small. And so for instance, like the rational numbers is definitely not Galois small because there's infinitely many quadratic extensions of the rational numbers. Okay. Yeah, so let me just end with some exercises here. So I claim that, so this is just a group theory fact, finitely generated discrete groups are small. This I think is like coming down to the fact that if you have a finitely generated free group, it only has finitely many subgroups of any given finite index, which I think is a standard exercise if you're studying free groups. If you use that exercise, you can prove that a topologically finitely generated profinite group is small. Okay. And then I just sort of wondered, this is true for profinite groups. What if I just take any topological group? If it's topologically finitely generated, is it small? That's a very random question. Let me end with these exercises. So suppose I have a p-adic field, so just a finite extension of QP. This is like one of the two kinds of local fields that we want to do class field theory for. So very, very not random. Let's take the absolute Galois group of the p-adic field. And so the first exercise is to show that that is small. And I claim that this is a standard result. If you translate that to saying this is a field of characteristic 0, so by translation, I'm claiming that a p-adic field inside a fixed algebraic closure has only finitely many extensions of any given finite degree. If you ever took a course with the structure theory of local fields, you look at the unramified extensions and then you look at the ramified extensions, and so this you can find this in my number theory 2 notes is what I'm saying. So that's a kind of standard exercise. There's some like Krasner's lemma argument for the ramified extensions anyway. A less standard exercise is that in fact the absolute Galois group of a p-adic field is topologically finitely generated. So that's a stronger statement. I think if you look around on the internet, maybe you can get some help for, it's not standard, but I think you can prove it. If you're clever, you can prove it using what you already know about the structure of p-adic fields. Anyway, from this and this enormous theorem of Nikolov and Siegel, I don't think you actually need the full strength of this theorem in order to prove this, but whatever, you do get that the absolute Galois group of a p-adic field is strongly complete. So what am I saying? I'm saying that every finite index subgroup of the absolute Galois group of a p-adic field is open. Exercising Milne's class field theory, that is definitely not true for a global field. So a global field does have finite index subgroups that are not closed. Okay, so that's a contrast. And then finally, what about, so this was one type of local field. These are the, what's a local field for us? A local field is a field that's complete with respect to a discrete valuation and has finite residue field, right? And so there's the p-adic fields, and then there's the positive characteristic such fields, and those are all, by number theory 2, those are all isomorphic to Laurent series fields over a finite field. And they really work differently. So this exercise, this is a nice exercise. There actually are infinitely many non-isomorphic degree P separable extensions, even Galois extensions of this type of field. Okay, so that's, I can't remember if that came up the last time I taught number theory too or not. Using Artin-Schreier theory is the way to do this. Okay, so maybe I'll bring this up. It's actually related to Galois cohomology if you want it to be, and we're about to study Galois cohomology, so we can do that. Anyway, so this is a surprising fact. Okay, so therefore, whereas the absolute Galois group of a p-adic field is small, the absolute Galois group of a Laurent series field is not small, and this didn't have anything to do with inseparable extensions. There were even too many degree P separable extensions. And so as a result, it is therefore the absolute Galois group is not guaranteed to be strongly complete because we only know a priori that a topologically finitely generated profinite group is strongly complete. I think as a rule of thumb, if you have an infinitely topologically generated profinite group, unless you got it by taking the profinite completion of a discrete group, in which case it has to be strongly complete, you expect it not to be strongly complete. Okay, so that's kind of asking too much for an infinitely generated profinite group. And so I ask you the question, is it the case that every finite index subgroup of the Galois group of a Laurent series field over a finite field is open or not? Okay, that's my introduction. And then now this sets you up to look at the, again, there's like, I don't know, on the order of 10 problems involving